So, Scott and David, are you hearing me?
Yep.
Okay. David?
Yeah, I'm good.
Okay. So we are like 3 here, or I think anyone else was coming as well. Somebody else was coming, I think. Let me see.
One guy said he was going to be like half an hour late or something like that.
Okay, and what was the name of him? Do you remember the name?
Kyle, I think.
Okay. I only have your email addresses. I didn't know your names. So I know David, Scott, and the other is Casey Volney at stlakeheadu.ca. I don't know what.
Yeah, that last guy, he said he'd be half an hour late.
30 minutes late? Okay. Okay. So just give me a few seconds and I will be back. We will start in a few seconds. Okay, both of you guys are having the screen. Are you able to see the screen now?
Yep.
Yeah, I see chapter 16.
Okay. I decided to start from chapter 16 as I know you are all having chapter 5, chapter 6, and chapter 16 for your final exams. If that is the case, please let me know because I have managed to cover chapter 16 today and the other chapter, the rest of the chapters tomorrow. So is that true, or we have to cover any other chapters as well?
Those are the 3 that we went over after the midterm. So yeah.
Right. So you also have any questions from the previous parts before the midterm?
I don't.
No.
You don't know?
No, the beginning stuff I get now.
Okay. Oh, you're okay with the beginning stuff.
Yeah, yeah.
Okay. Okay, so we will start from chapter 16. I hope you guys have already studied the material of this chapter, but let's go and have a general idea and overview of what happened in the 16th chapter. So in this chapter, you are basically confronting with 3 mechanisms of heat transfer: conduction, convection, and radiation. And for each of them, you have only one formula. For the conduction, you have, let me use my pen here. So for the conduction, you have to be familiar with the Fourier's law. For the convection, you have to know the Newton's law of cooling, and for the radiation, we have the Estefan Boltzmann Law of radiation. And what really needs to be studied here is actually the terms which are affecting each of those kinds of mechanisms. For example, for conduction, you have 3 terms. You have to know about the conductivity constant, which is K. It is really specific to different kinds of materials. My voice is returning back to me. I don't know why. So K is specific to the kind of material which is inside or between the 2 surfaces that are conducting and transferring heat to each other. A, which is the area that is effective between those 2 surfaces. The temperature difference between those 2 surfaces, as you can see here, we have a flow of heat from the left surface to the right surface. and there is a decline in the amounts of temperature. And also another term in the denominator of this fraction, which is the length between those two surfaces. And all in all, you have four terms for the conduction mechanism. For the convection, no. Before going to convection, we also have to mention out some points here as well. So I told you that depending on the kind of material you have, for example, if you have copper with a constant of 401 watt over meter times Kelvin, it really takes a higher amount of energy or higher amount of heat to be transferred from the left surface to the right surface, compared to the case here, for example, when we have silicon with a lower amount of conductivity constant. So basically, each of those terms are making their role in the total amount of conduction, and the only term that is actually making conduction happens later is the length between those two surfaces. The other terms, which are the constant, the area, and the temperature difference, they are all in line with the increase of heat conduction as they increase. Next slide, it also is telling you the thermal conductivity of different materials. As you can see, it is like much more higher for the solids with respect to liquids and the rest, which are the gases. That is basically due to the distance between the molecules of solids, liquids, and gases. In solids, for example, you have a shorter distance of molecule distance. So this molecules are much more closer to each other. So that's why they can transfer the energy much more faster by vibrating and different kinds of movements. But in liquid or gas, this distance is higher. It is a higher amount of distance, so the conduction happens much more slower, basically. So another term to be mentioned here is the thermal diffusivity. Thermal diffusivity is actually the tendency of my material to absorb or to transfer and conduct the energy. So, for example, when you in Canada, in winter, for example, when you get cold, it's very cold outside, like -30, and in the inside temperature is like 20 degrees. So if you are walking and then you don't have any coat, what you actually do is to hold your arms and make yourself much more dense in terms of posture, and that makes you have a lower amount of diffusion, basically diffusivity, because the denominator of this fraction here, if you see the heat storage, it isn't working, I don't know why. Okay. The heat storage, which is in the denominator, is making its role in stopping the heat from conducting or transferring. But the numerator of this fraction, which is heat conduction, that comes with the constant of K, is trying to conduct the heat, and in challenge with the denominator, which is density times the specific heat, which is C of P. So basically, if this amount, which is alpha, is larger, then the propagation of heat will happens much more faster. If it is lower, the heat propagation happens much more slower. Next mechanism of heat transferring is convection. Convection is really solely limited to the cases where we have a surface and a medium of liquid or air is transferring over it. So if you remember, in conduction, we had these like vibrations and motions of the molecules that happen to help the conduction and transferring of the heat. But in convection, if we don't have any like motion in the medium of liquid or air here, as you can see, we have an airflow here, or liquid can pass through the hot surface, then the convection won't happen, because it really depends on the wind speed, the specifications of the air which is moving around, and this is the kind of heat transferring between conduction and radiation, which we go through in a couple of slides. So this was convection, and convection really the rate of convection is really dependent on how we are transferring the heat, or how we are like absorbing heat from the surface we are talking about. For example, if we have a hot egg here, then hot egg, then by natural convection, so due to the, for example, difference of density between the different locations of air, there would be a like flow of air from the places which are like less dense to the places which are much more dense. So this will make a flow of air, and this flow of air will cool down this hot egg. But this kind of like convection, which is natural convection, mostly has like low amount of transferring rate in terms of heat transfer, because it is basically natural, as it is saying. But in forced convection, we do have like fans, or we may have turbines, fans, and it really has the goal to cool down the surface much more faster. So that is basically the difference between forced convection and natural convection. Forced convection is being made by external means, but natural convection are mainly caused by buoyancy forces or the density differences. So it is not in our hand. It is not in the human's hand. Convection also has a formulation of convection heat transfer coefficient, which is H. It is denoted with the term H here. So, oops, what happened here? So I have to, okay, I can't do anything about it now. If you can see, the convection constant is shown with H. So why does it, it doesn't, okay. H is the convection heat transfer coefficient. It is really comparable with the one which we had for the conduction, that was denoted with K, if you remember. So here we have H instead of K, and we again have the area. So area is always in our heat transfer equations, even if it is for like conduction, if it is for convection, or it is for radiation. And the next term is the temperature difference between the surface and the medium which is transferring over it. So basically three terms. compared to the 4 terms we had for conduction. Okay. Next mechanism is radiation. Actually, radiation is the energy emitted by matter in the form of electromagnetic waves. So we had molecules movements, we had the transfer of heat from the surface to the medium over it, but in radiation, actually, we don't have any medium. It is the transfer of heat in the form of electromagnetic waves. And that is the result of changes in the electronic configurations of atoms or molecules. For example, if you remember the free electrons in atoms, they get energy, they go to a higher energy level, and then when they come back to the lower levels, they emit a package of energy, and this package of energy will be in the form of electromagnetic waves that will be transferred all the way to the other surface, and it doesn't really need any medium or substance in between. So it says it doesn't need any intervening medium in between. And any other points to be mentioned out here? Yeah, we have to know that all bodies that have temperatures over absolute zero. Absolute zero means 0 Kelvin. All bodies over 0 Kelvin emit thermal radiation, basically. Only bodies that are at 0 Kelvin, they do not have any radiation. And that's basically impossible to reach 0 Kelvin. If you go and search it, you will see it is impossible to get to that point. At least so far, it was impossible. So radiation is a volumetric phenomenon. In all solids, liquids, and gases, it happens. But in our case, we are confronting the questions with the surface configuration. So when we have solids, we consider that radiation is happening from the surfaces only. For the radiation, we have this Estefan Boltzmann Law that has 4 terms. It has a sigma Estefan Boltzmann constant equals to 5.67 times 10 to the power of minus 8. And again, we have an area term here. That is the area, the surface area that is emitting the energy or the radiation. This is the temperature of the surface, Ts to the power of 4. That is actually telling us how the temperature is affecting radiation. If you remember, for convection and conduction, we had temperature term with a first order like effect, but here we have Ts to the power of 4. So if I, for example, add up 1 degree of centigrade to my temperature, then it will increase the heat radiation or the heat rate for powers higher, 4 powers more than what we had for conduction and convection. It really depends on the kind of surface that the heat is being emitted from. If it is, for example, if you have this feeling in summer when you go out, if the color of your t-shirt is black, you feel much more hot inside. Compared to the case you have, for example, blue or red or orange. That is actually why many people prefer to put on colored t-shirts and clothes in summer. That is because black surfaces, they have the most or the highest level of absorption and also emission in terms of radiation. So this epsilon is doing this effect is making its role as this effect for specifying how or what fraction of the total energy is being emitted based on the kind of that surface. So you can see different materials here have different emissivities. This term is called emissivity, and it is different for different materials. For example, black paint, it is really close to 1. For the white, it is a bit lower. For the skin, it is really close to 1 again, while we can see, for example, lower amounts for like copper or gold and aluminum foil here. So epsilon is showing basically what is the fraction of the total energy being emitted from that surface depending on its material. It is a value between 0 and 1. A very important thing to look at here is the Blackbody term. So when you are seeing the Blackbody term, you shouldn't think that Blackbody term is meaning when you have like surface with a black color. That is not the meaning of Blackbody. Blackbody is the surface or the body that has the highest level of absorption and the highest level of emission, as I told you. But the color, in terms of color, they are also like very similar with the definition we have for the Blackbody. I mean, if for example, T-shirt is much more blacker, or if it is much more closer to the black color, the emission term is much more closer to the black body, but it doesn't mean that it really is a black body. So if I have a black T-shirt, my black T-shirt is not a black surface. That is really important to know. So as you see in the problems, you have to know that the heat radiation, which is coming from, for example, the sun, is not totally absorbed. A portion of it, which is the term alpha, that is the absorbivity term here, is being absorbed, and the rest is being refracted to the surrounding. So if I'm solving a question and it is asking me, for example, we will have this question in a couple of minutes. We have an insulation layer here. Then there is a heat radiation, and this amount of radiation is not totally absorbed. A portion of it is getting absorbed in the inner layer, and the other rest is refracted to the surrounding. And this layer is also isolated. So what does that mean? It means that there will be no transfer of heat from this layer to the inner layers of this surface. So what happens? The thing that is happening is this amount of absorbed heat should be transferred back to the surroundings in the form of convection, because we do not have any radiation term here. The radiation has happened. Now there is no other surface to have conduction with. So what happens? The surrounding, for example, is air. We only have the convection term that is the only way for transferring this amount of absorbed energy. So that's absorbed energy, which is all alpha times the input radiation term, should be equal to the Q of convection. We will see it in a couple of minutes again. The net radiation heat transfer is basically the difference between the radiation of two objects that are completely enclosed in a very big area. For example, if we consider a surface here and we enclose the boundaries uh, of the outer like surroundings with a like cloud here, we can see that the radiation emitted by this surface is going to the boundaries of this like cloud, and it is being transferred back in terms of radiation again to this surface. So the difference between the radiation of the surface and the radiation of the outer like boundaries of that cloud will specify what is the net transfer of heat between those two um, surfaces or bodies here. Again, we have the epsilon term, we have the sigma, which was the Estefan Boltzmann constant, the area, that is the area of the surface, and the temperature of the surface, and the surrounding temperature, that is a temperature at a location far away from the surface. It is really important, especially in the convection. For example, when you have let me draw it for you here. When you have a convection problem, it is really important to put the surrounding temperature that is far away from the surface you are solving your heat transfer problem for. So if I have a surface, and so if I have a surface, then I want to find the heat convection. There is a like velocity of air or liquid based on the medium we have, is air or liquid above the surface, and the surrounding temperature is being at a location far away from the surface temperature. Sorry, surface temperature. So we should choose this temperature when we are substituting it in our equation. That is because if you use the temperature that is still inside your velocity profile here, this temperature is changing actually from the surface to the surrounding. So you have to put a temperature at a location that is far away from your surface, that the surface is not affecting it. That's what it means. If you put the temperature at a close location to the surface, then that temperature is actually still changing if we go up in terms of location. So it is really important because the temperature is a continuous function. It cannot, for example, drop suddenly from 20 degrees all the way to minus 30 degrees. It is not like non-continuous. It should be a continuous function. It really depends on the material and the kind of heat mechanism, whether it is conduction, convection, radiation, that how it changes or declines or increases. But it should be a continuous function. It cannot be non-continuous. So you have to put the temperature that is the final temperature. It is not, for example, changing anymore. If I am, for example, putting this temperature, then again, if I continue going up further, the surrounding temperature wouldn't change. So that is the temperature, the surrounding temperature I will use in my radiation or convection problems. So this was, I think, it wasn't the last slide. We have still 2 more slides here. Okay. Okay. Solving the heat transfer problems, in most of them, you should be able to combine different mechanisms of heat transfer together, because there is no problem where you have only radiation, or for example, you have only convection or conduction. They should be combined together for solving a question. So that's why you have to be able to find the combined heat transfer coefficients that makes the problem much more easier for solving for you. For example, if we have a surface, as it's saying, we are intending to find the heat transfer between a surface and a gas in terms of convection and radiation. We have a surface, there is a gas over it, and we do have both convection and radiation. It is really hard to write with this pen. And convection. Okay, you know that. And for having that term, what you do is to first find the heat transfer, the total heat transfer of convection and radiation, and add them up together. The convection heat is denoted with the H of convection times the surface area times the temperature difference between the surface and the surrounding. The next term, which is for radiation, is the epsilon, which was the emissivity term, times the Estefan Boltzmann constant times the area, the surface area, and the next term is each of those temperatures to the power of 4 minus together. So if I want to find a combined heat transfer coefficient, what should I do? I should write the total equation as a H of combined times area times the temperature difference. If you had paid attention enough, you know that in all equations so far, we had the temperature difference and the area term. And also we had a constant that was before them. For example, conduction, you had K. In convection, you had H. And for the radiation, you had this emissivity term, that Estefan Boltzmann constant. The only difference was that the temperature difference term was the subtraction of the force power of those temperatures from each other. So if you want to find a total heat transfer coefficient, what you do is to consider a combined H, and the rest of the terms that are the temperature difference and the surface area are the same as what we had previously. So if you substitute this amount instead of this term here, and you subtract the common terms from each other in the left and hand sides, then you would have H of combined as H of convection plus sigma times epsilon times this term, which is actually Ts to the power of 4 minus T of surrounding to the power of 4 over this term, which is Ts minus T of surrounding. So it is your H of combined that is being used in the problems where you have a combined term of convection in line with the radiation term. So basically, it was a summary. It was the whole thing we had for radiation. We have the Fourier's law of heat for conduction. We have Newton's law of cooling for convection, and we also have a Estefan Boltzmann law for radiation. There were also some terms for conductivity and convection. Arsalan is calling me. Let me answer him now. Yes? Okay. I will do that. Okay. It seems we have Kyle here. So let me add him. Kyle, are you hearing me? Yes, okay. We will continue. We have, when you were not here, we covered a general idea and overview of what we know from radiation, conduction, and convection. We went through, let me just go have a quick overview, like 1 minute or 2 minutes of what happened in this chapter. We started from the 16th chapter. Basically, we intend to solve problems from this chapter today. So let me share my screen now. I don't know why it isn't showing up. Share my content, start broadcasting, and okay, we covered the terms for conduction. For conduction, we had like, let me use my pen here again. We had these 4 terms: the constant of conductivity, the area of the surface you're talking about, the temperature difference in the numerator, and only one term, which is the length or the distance between those 2 plates in the denominator, that is affecting the total heat rate in an inverse manner. Like if I have a larger or a higher amount of length, that then the heat conduction would decrease. So we covered the thermal diffusivity, and we said it really depends on the tendency of your material to absorb and like keep the energy or heat, or transferring it to have a higher or lower amount of thermal diffusivity. If it is more conductive, or it is more eager to transfer the heat, then the heat conduction term is much more higher. If it is more eager to keep the energy, then the term in the denominator, which is density times the specific heat, will stop the heat from transferring, and that would result in a lower amount of thermal diffusivity. The next kind of mechanism was convection. In convection, we had forced convection and natural convection. Forced convection is actually referred to the systems where we have external means of like transferring heat, whether we have a fan or a pump or a turbine. In natural convection, you do not have any external means. There is only differences in density, or it is due to the buoyancy forces, which will make the heat from like going from the hotter surface to the colder surface. And the equation for the convection is really, really similar to what we have for the conduction. Instead of the, if you remember, it was K times A times temperature difference over length. So instead of K over L, we have H here. And the area term and the temperature difference term are again embedded inside our equation. For the radiation, we said it is the kind of transferring, heat transferring, where there is no like molecules movement or like vibration in my vibration of the molecules. We don't need any medium in between. It is in the form of electromagnetic waves that the heat is transferring, and all bodies with a temperature over 0 Kelvin can emit and transfer energy. And again, the equation for heat radiation is again much more similar to what we had for conduction and convection. We have a Estefan Boltzmann constant, area, and also temperature to the power of 4. We have also another term that is the emissivity term, epsilon, that comes from the fact whether the surface of the body we are talking about is eager to transfer the heat or absorb it. It is very, very like similar to what we had for the thermal diffusivity in the conduction slide we had previously. It is saying, for example, if a body is going to absorb the energy or transferring it. We talked about the black like t-shirts, which are not like suggested if for putting off when it is summer, because colored surfaces, colored t-shirts are less eager to absorb the energy, and they refract most of the radiation which is coming from the sun. But the black bodies are much more eager to both absorb and emit the energy. So we talked about the term of black body, which I which I said is called to the surfaces that are at the highest level of emission and absorption. So it is both. When a body has an epsilon equal to 1, it has the highest level of absorption and also emission. When we have when our body is not a black body, then the epsilon is an amount between 0 and 1. So it is basically dependent on the amount of epsilon how our heat rate would change. Again, we had these concepts here, and we are now, I think, ready enough for going to the problems. So let me see what I have here. Okay. I only have the selected problems and also a few final exams of your previous semesters. I only had them, so I have selected the questions based on them. If you have any other like questions for sharing, please, you have my email. If you don't have, I will provide you with at the end of this session. You can send me and we will go through them at the end, or if we didn't have time today, we can do that tomorrow. For the 16th chapter, I have selected 4 questions for solving in the example problems you have in your website, or Moodle, you call it, here call it Moodle. The first one is 1682. Just to check up again, everyone is seeing the screen? Please type it down.
Yep.
Or
Yep.
tell me. Yes? Okay. So first question is telling me that an electrical power, let me use my pen here. The bad thing is my pen is very wide. I cannot write very sharply. So an electrical power is required to maintain the surface temperature of an electrical wire submerged in boiling water at 115 degrees of Celsius. So what is the question here? So the question is in the first part of this sentence. The electrical power required. So what is the required electrical? Now it's better, I think. So when it is saying how much energy or how much electrical power I require for maintaining the surface temperature of an electrical wire submerged in boiling water at 115 degrees Celsius, it means the surface of my wire is actually losing energy, because it's saying how much energy I need for maintaining the surface temperature of it. So if there was no energy loss, if there was no heat loss, then what was why would I need for like giving the energy or the voltage to this wire for keeping its surface temperature? So actually that means I am kind of losing energy from the surface of that wire in a way that I need to put and put at the input like energy for maintaining the surface temperature of it. And I have to calculate the amount of energy it is losing before calculating how much energy I would need for maintaining the surface temperature of it. And I am seeing that the wire is being submerged in a medium of liquid. So what is the only way of heat transfer I would have here? I think the only one is convection, because in terms of conduction, you don't have like any other like solids besides this wire. So that could be considered to be negligible. But in terms of convection, we know that when we have a flowing medium, it can be considered that the medium is like flowing, because the size of the wire is like much more smaller compared to what we have for the whole like medium here. So it can be considered that the only way of heat transfer is convection here. So what I have to basically first do is to know what are the sources of energy that are coming inside my system and are going out of my system. This is the most important thing you have to specify in all questions, not for today, but only for the chapters of the chapters 5 and 6. The only terms we have here, one of them is coming from the electric source here, which is due to the voltage and current I have from the power from the like from the electric power I have in my home, in my room. And the other term is the convection that is actually between this wire and the liquid. I don't know why I can't use a smaller pen here because it is very, I cannot show it here. Let me show it on my notepad. So if you have, for example, heat source here, it is being submerged in a liquid of water, then your surface control or your system is like the boundaries of this wire. In the boundaries of this wire, you have an input. The input is coming from the power, and the other is the Q dot of out, which is being transferred out to your medium. That is equal to the convection term here. So basically, if you write your energy equation, you know that there is no, if we consider that there is no leakage or there is no loss in terms of energy, all of the energy that is coming to this like a wire should be transferred out to the liquid. So there is no changes in the internal energy and temperature or like conditions of this wire. That means we have a steady like condition for this wire. There is no change in the specifications and conditions of this wire. So the rate of changes in the inside energy of this wire should be equal to 0. So what other terms we have here? For the inside, for the input term, we have W dot E, which is the work being done by the power. And for the output, we have Q dot of convection. So what we have is actually two terms that should be get equal together for solving this question. That is how the writer is solving this equation here. So let's first go through the assumptions here. So basically, it is assuming that a steady operating conditions exist. A steady operation condition is actually telling me that there is no change in the temperature or any specifications of this wire, so that the net energy difference inside my system is equal to 0. So that is why I only have two terms. The first assumption here. The second one, convection heat transfer coefficient is uniform. What does that mean? It means that the H, which is the convection heat transfer, is not dependent on the temperature or any other specifications of that liquid. Because when I start like empowering my power is coming. At first, the temperature difference, for example, is 10 or 20 degrees of centigrade. But after working a few minutes, then the temperature of the liquid or the medium around the wire would increase. So after that, the temperature of the liquid would be much more higher. And we know that both the H and the K term, which is the conduction constant for the conduction heat transfer, they are dependent on the temperature somehow. In most of the problems, we consider that they are constant, or we use the average amounts of them to simplify the solving of the solution of the question. But basically, they are dependent on the temperature. And that assumption is actually telling me this H term is not a function of temperature. It is a constant. So that is why I can use the convection formula, which is H times area times temperature difference. Next assumption is heat transfer by radiation is negligible. That is I think, very obvious here, because when we are talking about, for example, two surfaces that are very close together, talking about radiation is really like not logical, because radiation is uh, effective when you have, for example, two surfaces and two objects that are far from each other. Not it is not only for objects that are far from each other, but uh, the material between them is actually air, or for example, it is kind of an isolated material. When we have a medium like liquid or solid, talking about radiation is not considered in most of the questions. Next is heat loss from the boiler is negligible. That means that my whole system, which is the boundaries of this container, there is no loss of heat from the boundaries of this container. It means that all energy, or all of the heat that is being transferred from the wire all the way to the surrounding medium, which is the liquid, is solely making the temperature of that liquid to go and rise. It doesn't transfer or go and escape from the boundaries. Because if we want to consider that term, that then there needs a higher amount of energy, for example, for increasing 1 degree of Celsius for the temperature of the surrounding liquid, because all of the energy is not being transmitted to the liquid. So that was the last assumption we had here. So as I said, we have only two terms. We have to specify the convection term, and on the other side, we have the power which is coming from my wire. So what I do here is I will use the Newton's law of cooling by substituting the amounts of convection constant, which is H, surface area, and a temperature difference. I would have an amount of, like, for H, so for H, I have this amount of 51,250 watts over meter squared times Kelvin. It is coming from the average of the upper and lower values for the convection heat transfer coefficients given in table 1655. It is really important here, because the most challenging part in all of the questions for you is to read from the tables, because all of the equations and the other things, they are all like coming from your logic. If you have a good logic and you can specify what is the heat sources, what are the heat losses inside my system, and write down your equations, the only part that is challenging is to go and find the values of the constants from the charts. I really don't know where is this table 16.5, but I really don't have it here, but you may have it, and based on that you can go and check the convection constant for different, for example, liquids. For water, for air, it is dependent really on the substance or material you are talking about. And the area of the surface is being calculated based on the periphery of that wire. So wires are mostly in the shape of cylinders. And for finding the total area, the total effective area of cylinders, you have this periphery that is being calculated based on like this has a diameter of d with a length of L, so the area around this cylinder is equal to the perimeter of this circle, P times D times the length, which is equal to P times D times the length. That is what you see here. P times the diameter of the wire, which is 1 millimeter, 10 to the power of -3, times length, which is 15 centimeters, is equal to 4 times 4.7 times 10 to the power of -4 meters squared. And substituting that amount in the convection heat rate, I will have H times A times the temperature difference, which is which is 115 minus 100. That is actually the amount of the temperature of the water, and that is the temperature of the surrounding air. That would give us an amount of 362.2 watts. And the question was asking me what is the electrical power required. So the electrical power required, as I said, should be equal to the heat rate by convection that is being calculated as the heat which the liquid is losing from the inside, like 115 degrees of boiling temperature, to the outer space of 100 degrees of Celsius. Let me see what is next here. Okay. Okay, any questions if you have so far? We'll go to the next question, which is again a transfer of heat that is being made by convection and radiation. So let me minimize myself here so that I can see the whole screen. Again, it is asking me the power required to maintain the soldering iron tip at 400 degrees of Celsius has to be determined. So the question is limiting my site of view to only the iron tip, as it is asking, as it is saying. So basically, I do not have any like work with the other rest of this soldering iron. I only I'm working with the tip of it. And it is saying how much power is required to maintain it at 400 degrees of Celsius. And if you see at the picture, it is giving me a surrounding air at 20 degrees of Celsius, and also conditions for the surface temperature of the tip and the length and diameter of the tip. So basically, when it is giving you the specifications of air, and it is saying the air is at 20 degrees of Celsius, you are having two terms of heat transfer here. One is convection, the other is radiation. Because radiation happens because the air is making an enclosed like area between the surface and the total like surrounding of it. And the convection is happening because the air is actually flowing over this tip of this iron thing. That is because one may ask, for example, why the air is not stationary. If the air is stationary, then there would not be any like convection term, as we discussed earlier. But for sure, we have air convection around this iron tip. That is because when you have a hot surface, then the density and the specifications of the air around this like tip will change if we want or if we don't want. Because the molecules which are around this tip, they are being much more hotter in terms of temperature, basically with some low amounts of conduction heat transfer. And that makes the air around this tip denser than the air at the other locations. And the difference in the like density and these terms will make the air to flow and to move around the tip of my iron, like soldering iron here. That's why I would use a convection term here. So for finding the convection and radiation, I have the formulas, but the first thing to know again here, when you are solving questions, the first thing you should consider is to depict a diagram and try to understand what the question is asking you. So the question is having like, I don't depict the rest of it. I only show the cylinder tip of this soldering iron. So the question is, what amount of power I should put in so that I can keep the temperature, the surface temperature of the tip at 400 degrees of Celsius, because it is losing energy in terms of convection and radiation. So I have convection, I have radiation, and I have an input energy term that should be calculated. So if I write the equation, the energy equation for the boundaries around this tip, I will have the change in the amounts of inside energies is equal to 0. So everything that is coming inside is going out. So inside energy is equal to input energy is equal to Q of convection plus Q of radiation. So for both kinds of heat transfer, both radiation and convection, I have the surface area, which is the common term between them. So first thing I have to calculate is the surface area. That is a bit tricky here, because if you see one side of this tip is attached to the rest of this soldering iron, so that this part is not in contact with the surrounding air. That is why I should not consider the area that is related to one circle that is being attached to the rest here. I should only put one circle that is in contact with the air, and the area which is at the periphery of this cylinder. So the total area would be pi times d to the power of 2 over 4, which is for the only circle that is in contact with the air, and the area that is around the area around the cylinder. And that would be equal to pi times diameter, which was equal to 22.5 millimeters. So 2.5 times 10 to the power of minus 3 will be 0.0025 to the power of 2 over 4 plus pi times diameter, which is again 0.0025 times the length, which is 20 millimeters. That is again converted to meters. That would be equal to the total area of 1.62 times 10 to the power of minus 4. For convection, what you do is that you should first go and check what is the convection constant for air at 20 degrees of Celsius. I think that should again be available in the table named 16.5. 16.5. If you have time, we will go and check that at the end. But in that table, you can find the convection constants of different fluids. By fluids, I mean liquids or gases at different temperatures or different specifications, maybe. That is equal to 25 watts over meter squared times degrees of Celsius times the area, which was previously calculated as 1.62 times 10 to the power of minus 4, times the temperature difference, which is 400 at the surface, all the way to the surrounding air, that is 20 degrees of Celsius. That will give me an amount of 1.54 watts. This was for convection. For radiation, what I have to first find is the emissivity constant. If you remember, for the convection, I had this formula: epsilon times sigma times A times surface temperature to the power of 4 minus the surrounding temperature to the power of 4. So in this equation, the Estefan Boltzmann constant is always constant. So it was equal to, I think, 5.67 times 10 to the power of minus 8. I don't remember the unit of it. We can go and check it back again. But for the emissivity term, it is really depends on how much your surface or substance is close to the black body. If it is a black surface, if it is, for example, a human body, or it is a black t-shirt, it is very close to 1. But if, for example, it is a fiberglass or other materials, we check them up, is something between 0 and 1. What you have to find here is that you should go to the tables and check for the material you are asked and check what is the emissivity constant for that. Since it is telling us it is an iron tip, so you will go and see what is the amount for iron. I think we had it in our slides here. As you see, for iron, no, it is not covered here. So what you will do is that you will go and check what is the amount of emissivity for iron. I think that should be available in the 6th table of the 16th chapter, maybe in the Cengel book. But for now, we will only substitute the amount of it, which is 0.8 for iron. And for the Estefan Boltzmann constant, sorry. You have this amount of 5.67 times 10 to the power of minus 8 watts over meter squared times Kelvin to the power of 4 times area, which is 1.62 times 10 to the power of minus 4 meters squared, and T of the surface, which is 400 degrees of Celsius to the power of 4. The most important thing here is that you should convert all amounts from Celsius or degrees of centigrade all the way to the Kelvin system. When you had convection or conduction, it was not important. That has a simple explanation. I don't know if every one of you know. That is a good question. Can anyone answer this question? Why in conduction and convection it was not important for using Kelvin or Celsius? Both of them were the same. Anyone?
Because the difference between them is the same.
Yes, exactly. So actually the temperature difference, which was T of surrounding minus T of surface, sorry, T of the, it's again not working very good. So delta T was equal to T of surface minus T of surrounding. So when you, for example, use Celsius degree, then for example, Ts minus T surrounding in Celsius. Then we convert it to Kelvin. So we add it up by 273 minus T of surrounding plus 273. These two terms will remove out each other. So again, the temperature difference in Kelvin and centigrade are both the same. So it was not important for us to choose each of them. But when we have radiation, it is like Ts to the power of 4 minus T of surrounding to the power of 4. And here it is really like we can change it to T S minus T surrounding times Ts plus T surrounding times Ts to the power of 2 plus T of surrounding to the power of 2. That is coming from the equations you know from mathematics. And except this term, and also, no, even not this term and this term. The 273 value, the 273s will not remove out each other in those two terms. So that is why basically we have to convert degrees of Celsius to degrees of Kelvin. You may ask why we don't use Celsius and we use Kelvin. That is because if you go back to the definitions of radiation, surface bodies start radiating when they are when they have a temperature over 0 Kelvin. Because 0 Kelvin is actually the temperature that is actually the lowest possible temperature at which the molecules are stationary. They don't have any kind of movement. So there won't be any like emission of energy from the falling of electrons from higher like levels of energy to the lower levels of energy. And in that case, there won't be any like transfer in energy. That is why we are using the Kelvin system. So for radiation, it is very important for substituting Kelvin amounts. That was a side point we mentioned out here. And by substituting the amounts of temperature for I don't know why. Yeah. For the surface at 400 degrees of Celsius and 20 degrees of Celsius for the surrounding, we will get 1.45 watts for the radiation term. That is 1.45 watts. And adding up it and combining it with the term we have from convection, adding these two terms together will give me an amount of approximately 3 watts for the total amount. And that is basically saying each of the convection and radiation terms, they were very close together. They had both 50% of the total energy share. It is really important because at the end of many questions, they may ask you what is the fraction of, for example, heat transfer that is being made by conduction. What is the share of, for example, heat transfer made by radiation? And in many cases, it is actually being made. I mean, the most the most amount of energy is being transferred by convection. This is the case when you have a low emissivity, for example, term. As it is saying, for example, here, if the iron tip was polished with an emissivity of 0.05, that means this term, which is emissivity, decreases. Then the power required to maintain at 400 degrees of Celsius would reduce to 1.63. That is only a few like percents over 1.54 that is being made by convection. That means like share of 90% of energy is being transmitted only due to convection. So that was again a question they may ask you, because based on what is the emissivity term, what is the temperature difference, the share of energy between those two kinds of like radiation or convection can change. But so far what I've seen in most cases, the convection term is much more higher, because it is for example, think you have a rod, you have a hot rod, and you intend to keep the temperature, the surface temperature of it at a specified amount. The best thing to do is to try to make the constants that are in your hand as low as possible. For example, you have the emissivity term in your hand. You have, for example, the K, for example, conduction constant in your hand. These are the variables that you can change. Many things you are not, they are not in your control. For example, the temperature difference, the Estefan Boltzmann constant. They are always the conditions that the problem is exposing to you, that the problem is controlling. You have no control of that. So what you do actually is to try to reduce, for example, the emissivity term in a way that the least amount of energy would be transferred from the tip of that, for example, iron to the surrounding. That is how you will reduce the amount of energy you would consume for keeping the temperature of the surface you are working with. And that is why in many cases the convection term is much more higher than the radiation, because we always try to reduce the amount of emissivity constant in a way that the radiation term decreases in a very I mean, a good share of it would be decreased with respect to convection. If there are any questions, let me know. If not, we can go on. We still have two problems in the examples, and I have also selected 2 or 3 questions from the final exams for this part. 42. So we still have 1 hour to go. It is 18:25, and we also, I think, started 5 minutes later. So we still have a good time for covering what we have for today. So the question 1643. Let me read it. A 4-meter diameter spherical tank filled with liquid nitrogen at 1 atmosphere pressure and minus 196 degrees of Celsius is exposed to convection with ambient air. The rate of evaporation of liquid nitrogen in the tank as a result of the heat transfer from the ambient air is to be determined. What the question is asking me is basically okay. I have a tank which has a 4-meter diameter, and the tank is being filled with nitrogen. So basically the problem is a convection problem, because the tank is being put in a area of air at 20 degrees of Celsius, and the thing is the liquid inside of it is absorbing energy from the outer air. That is really simple to know, because as you see, the temperature of the nitrogen is specified at an amount of minus 196. If you see here, the nitrogen is kept at minus 196 degrees of Celsius, and the outer air is equal to 20 degrees of Celsius. And we know when there is temperature difference, we always have a flow of heat from the place of higher temperature to the one which has a lower amount of temperature. So basically, the energy from the air is being absorbed into the tank, and that amount of energy is transforming the form of my nitrogen from liquid to gas. As you see, the question is saying here, liquid nitrogen. So again, we have 2 terms. the convection term, that is between the air and the liquid, and an evaporation term that is changing the form of my liquid nitrogen to gas. So all of the energy that are being transferred from the outer like space is being absorbed into my tank, and that amount of energy is changing the liquid to the gas. And we know when we have evaporation, we have to find the evaporation heat from the tables. If you remember, it was also covered in your midterm. The amount of heat corresponding with evaporation is calculated based on what we have from tables, and is equal to enthalpy of gas minus enthalpy of fluid. And I think it is covered in I do not have the table on my tablet, but let me see if I can show you on my desktop here. Okay, let me go back to show you where you can find the amounts of evaporation. Okay, here we have it. Stop sharing, and then I will allow the other device to share. Okay, let me. I have it here. Okay, I have to first send it from my desktop to my iPad, and then I can show it on my iPad because I cannot activate sharing on the desktop right now. Okay, let's go back here. Screen. Okay, share content. So, yeah, if you go to the appendix of Cengel book, in the first appendix, the second table here, you have the boiling and freezing point properties for the nitrogen. As you can see, let me open it in another editor where I can use my pen. Okay, in the second table, if you check and find nitrogen here, you have nitrogen at a boiling point of minus 195.8, which is very close to what we have for our nitrogen now, 196, only 0.2 degrees of Celsius difference. So we can consider that our liquid, our nitrogen, our liquid nitrogen is at the boundary of liquid and gas. So we can use this information here. As you can see, the latent heat of vaporization, H of Fg, the subtraction of enthalpy of gas from the enthalpy of fluid is equal to 198.6. And going back to what we had for for our main problem here, you can see that we first have to find the convection heat transfer that is basically calculated based upon the convection constant of air at 20 degrees of Celsius, that is equal to 25 watt over meter squared times degrees of Celsius, as the previous case. Similar to the previous case, it is equal to 25 watt over meter squared times degrees of Celsius. The area, which is the area of the sphere, if you remember, the area of a sphere is equal to 4 times pi times radius of it to the power of 2, and that could be right as pi times 2r to the power of 2, and 2r is diameter, so it is pi times diameter to the power of 2, and we can use this area for calculating the amount of convective heat that was transferred. And for the temperature difference term, we can use the surface temperature of the tank. It is really important to know that when we are solving every thermodynamics heat transfer question, it is really important to write down the assumption. Here, we know that for sure the surface temperature of this tank is different from the temperature of the liquid nitrogen inside it. But the most naive and trivial explanation or consideration is to simply consider that the surface temperature of the tank is close or similar to what we have for the liquid nitrogen. That is basically the case when we do not have any information from the question itself. When they are not giving us enough information, we use simple considerations and assumptions for making the question easier to solve, because we do not have any information for finding, for example, the temperature of the tank around the liquid. We do not have, for example, any information about how the heat is being transferred continuously from the boundaries of this, for example, tank to the inside liquid nitrogen. So that is why we use surface temperature of minus 196 for the surface of the tank instead of what it may really be. that is also mentioned out in the fourth assumption of the question here. If you see the temperature of the thin-shelled spherical tank is nearly equal to the temperature of the nitrogen inside. So knowing that, we can find the heat rate, which is 271,000 watts, and that amount of energy could be used for finding the mass rate of evaporation here. That is what the question has asked us basically. The rate of evaporation of liquid nitrogen in the tank should be determined. So the unit of evaporation rate that we found from the table was 198 kilojoule over kilogram. And the heat rate that we found for convection is equal to 271,000 watts. And we know that watt is joule over second. So basically 271,000 can be converted to kilojoules over second. That would be equal to 271.43 kilojoule over second. And dividing the convection rates by the evaporation heat we found from the table will give us the mass rate, which is 1.37 kilograms per second. So when they are asking the rate of evaporation, the meaning or the translation of it is actually the mass rate, because for the evaporation, we do not have any external information rather than the evaporation difference of enthalpy that is being extracted from the tables. So mass rate times H of evaporation equals the heat rate that is calculated from the convection term. We have another question here as the last example, and after that we will go to the questions of the previous final exams that were actually corresponding with the contents we covered today. Last example from this side is considering the convection heat transfer coefficient, heat transfer between the surface of a pipe carrying superheated vapor and the surrounding is to be determined. So the question is asking me, what is the convection coefficient? That is basically H. The amount of H has to be determined. And other information is that I have a pipe which is carrying superheated vapor, and the superheated, so let me use my pen again here. So the superheated vapor is coming from the left side here. So it is called superheated vapor. And we know superheated vapor is so hot. So basically the question is telling me the transfer of heat is from the superheated vapor inside the pipe all the way to the outer side of the air which is surrounding my pipe. So the superheated vapor is coming from the left side and is exiting or escaping from the right side. and we have to find what is the convection H term here. So basically, the first thing to calculate here is to know how much energy this superheated vapor is losing throughout my pipe. That energy, that amount of heat, should be equal to the convection heat transfer that the pipe is transferring to the surrounding air. So if I again write and depict the picture of the problem, we should have let's use blue this time. So a pipe is considered, a superheated vapor is coming and is exiting. Throughout this, like the length of this pipe, the energy will be transferred to the inner surface of this pipe. And that energy is being again transferred to the outer air in a convection, like in a convection manner. So the surface, which is the interface, actually the interface of the change in the kinds of like heat transfer mechanisms, is the periphery of this cylinder. In the outer side, the superheated vapor is losing its energy. The surface, the inner surface, is absorbing it, and the outer surface of it, which is a few epsilons, like far from the inner surface, is losing this absorbed energy all the way to the surrounding air. So we have to say that the heat transfer, the heat rate coming from the inside is equal to outside, and inside and outside in this question is actually referring to the interface that is the surface of my cylinder. So if you consider the surface of my cylinder, Qn is coming from the superheated vapor to the boundaries of this surface, and it is transferring and escaping from the outer side in terms of convection. Q of out is equal to Q convection. And Q convection is equal to H times area times T of surface minus T of surrounding, and Q inside is equal to the amount of energy that is being lost from the superheated vapor. So we first have to find that amount. So as you can see, Q loss is equal to Q loss is equal to m dot, which is the mass rate, times the constant pressure constant, pressure constant times the temperature difference. Does anybody know why don't we use CV, which is the constant volume? Anybody knows here? Nobody knows? Okay. So for finding for finding the heat rate, which is actually the heat lost by the superheated vapor inside my pipe, I have to know what is the process my vapor is going through. In most of the cases, when you have a flow of like mass, you have an input mass coming in your pipe, and the other term, which the other another portion of mass which is going outside your system. You have to use constant pressure. That is because all of your medium, or all of your like liquid or vapor that is inside your pipe should have the same pressure. It is a tendency or the eagerness of your medium to happen at a constant pressure. We will talk about this in tomorrow more, but for just knowing today, it is really important for you to understand where a constant pressure happens, where constant volume happens, and it really needs some kind of thinking first before going into the details and calculations of your problem. For example, if you, for example, have a piston, and then you warm up this piston and cylinder system, since you have a moving boundary here, you have a moving boundary piston, the system is eager to go through a constant pressure procedure, because as you add up the energy, or as you add up heat into your like chamber here, every like epsilon very limited amount of energy will lead in the like vibration of the molecules. So molecules are getting energy, and they are much more closer together. They have higher temperature, and that will lead, and that will result in a higher amount of pressure. But they do not want to be close to each other. They intend to have the most possible distance from each other. This is really like similar to what we have nowadays due to the conditions of COVID. We intend to keep the most possible like distance from each other. That is what actually molecules are intending to do as well. So they will push the piston to rise up so that they will be in the same pressure amount they had previously. So that is why they intend to be expanded in terms of volume, rather than, or for example, in lieu of, instead of increasing their pressure. But if you have, for example, a tank where you do not have any moving boundaries, the system has no way. It is like being imprisoned. No, there is no way for being expanded. So in that case, when you do not have any velocity difference, because you are forced to keep your volume and be at your place, there is no place to be expanded and move. In that case, the procedure will happen in a constant volume manner, and the pressure will increase. Again, for example, for pipes where we have, for example, here, you have a incoming fluid coming from the left, and it is escaping from the right. So there is no, for example, restriction, or there is no pressure, or there is no force on the system to stop anywhere. The fluid is coming all the way from the left, and it has enough space to go away and escape from the right. So it is constant pressure. But if, for example, I have some kind of, I don't know, barrier here, so that the molecules have no way for escaping, in that case, we can say that the pressure would decrease, because if you, for example, see in the throttling valve, or for example, the faucet of your the faucet in your kitchen, it is actually a valve which is controlling the amount of liquid which is discharging from the pipe. In that case, the pressure is, the liquid is coming, and that barrier makes the molecules to decrease in terms of pressure. But when there is no barrier, when there is no like closed system, like a tank, where we have a piston and cylinder, in those cases, the mechanism is constant pressure. That is why we use CP instead of CV, basically. It is really important for where we have to use CP, where we need CV. So since my problem is a constant pressure problem, I will use constant pressure, and for constant pressure, CP is used, and temperature difference is 2 minus T1. Going back to the, so we will force those two right-handed equations to be equal together for finding the convection constant. And here, as you can see, m dot, which is the mass rate, has been given as 0.3 kilograms per second. That is being substituted in this location, in this part, and then C of P, which is constant pressure for superheated vapor, that is given by the properties. So the question has itself given me the amount of C of P. The specific heat of vapor is given to be 2,190 joules per kilograms times degrees of Celsius, times the temperature difference, which is 30 degrees. It is also again mentioned in the figure. So we find the total heat loss from the superheated vapor as 19,700 watts. This is the amount that should be forced to be equal to the heat to the convection heat that is being discharged from the surface of my pipe to the surrounding air, and that is how we will find the convection H term. Doing that, you can see H will be equal to heat loss that was previously found as 19,710 joules per second over the surface area, that is 1.571 meters squared. Again, that is the periphery of the pipe area, and the delta T, that is the temperature difference, which is surface temperature of the pipe, which is 100 degrees of Celsius minus 20, that is the surrounding air temperature. That will give me an amount of 157 watt over meter squared times degrees of Celsius. Again, it discusses that by insulating the pipe surface, the heat loss from the vapor in the pipe can be reduced. What it actually means. It says if we insulate the if we insulate the inner surface, if we insulate the surface of this like cylinder, then this heat loss would be reduced, because based on the material that the surface of this cylinder has, the superheated vapor will lose the energy of it to the surrounding like boundaries of this cylinder. If it is insulated, then the superheated vapor will keep its energy and will escape and go out of the surface, the boundaries of my system, without any loss. So basically, it doesn't change anything about the outer surface, because insulating the inner surface doesn't change anything about the convection H term. Even if you insulate the outer space, the outer like surface of this cylinder, then you will not have a very like effective change in the amount of convection, because the H term is mostly a function of the surrounding air, compared to being like a function of the surface that is transmitting convection. So by insulating, you basically are blocking the heat from transmitting from your inner superheated vapor to the surrounding boundaries of this pipe. So this was the last question for this part, as the last example. We have a few other questions, 2 or 3 other questions that are the ones asked in the previous session, in the previous semester's final exams. So okay, what? What we do here is again solve the question which is related to convection and radiation. So as you have already paid attention, most of the questions are the combination of convection and radiation in this part. So it is really important to have a good knowledge on these two heat transfer mechanisms. So let me okay. Okay, the question is asking us is first giving information on a spherical tank that is depicted in a 2D schematic, And it's saying that the internal diameter of this spherical tank is equal to 3 meters. And the material of the outer surface of this tank is made by a stainless steel that has a width of 2 centimeters with a heat conduction of 15 heat conduction coefficient of 15 watt over meter times degrees of Celsius, and it is used to store the iced water which is inside this tank at 0 degrees of Celsius. It's saying that the latent heat of fusion is 333.7 kilojoules per kilogram, and the tank is located in a room whose temperature is 22 degrees, so 22 degrees of Celsius for the outer space of the room, and the walls of the room are at 22 degrees as well. When the question is mentioning the walls of the room, it is basically referring to radiation, because when you are solving radiation question, it is really important to specify the objects that are transmitting like radiation together. And when it says 22 degrees of Celsius is considered for the walls as similar to what we have for the surrounding air of this tank, it means that there is no temperature difference between the walls and the air that is inside the room. So we use a similar amount of temperature for the walls, which is 22 degrees of Celsius. So this was mentioned here. And the outer surface of the tank is black. This means that the emissivity constant epsilon should be considered 1 for the radiation, because it is saying it is a black body. And the heat transfer between the outer surface of the tank and the surroundings is by natural convection and radiation. So the temperature of the outer surface of the tank is 4 degrees of Celsius. T at point 2 is equal to 4 degrees of Celsius. And the convection heat transfer coefficients at the inner and the outer surfaces of the tank are respectively 80 and 10 watt over meter squared times degrees of centigrade. So it means that I do have a pack of ice inside this tank, and I do have a convection between the ice and the inner surface of the boundary of this tank. And again, there is a convection term between the outer side of the tank and the surrounding air. And we also have a radiation term that is being extracted from the surface of this tank all the way to the surrounding air. So the question asks me to draw the thermal resistance network thermal circuit and label the associated resistances and temperatures. Thermal resistance network or thermal circuit is basically the network of thermal resistances which are very similar to what we have in, for example, electrical circuits as the resistance of the system over temperature difference. It is really similar to what we have for electrical circuits, where instead of temperature difference, you do have voltage difference. and the voltage is being transmitted from the place of a higher voltage all the way to the place of a lower voltage, and the current of this transmission is very dependent on the resistance of the circuit inside or between those two voltages. This is exactly the same for the same as what we have for heat transfer. In the heat transfer, if you have materials that are very like mm, uh, mm, uh, weak in terms of diffusivity, and they do not intend or they are not eager to transfer the heat, they will isolate and insulate your system so that the heat transfer will occur with a low amount of current. So current is corresponding with heat rate in thermal systems, and voltage is also corresponding with what we have temperature difference in our system. So if I have a correlation between these two systems in electrical systems, you have voltage between 2 points, and the current corresponding with this system is equal to voltage difference over the total resistance of the system. In heat conduction, in heat transfer, instead of voltage difference, we have temperature difference. So the temperature will be decreased through a system of thermal resistances from a place of higher temperature T1 to T2, which has a lower amount of temperature, and the resistance between those two temperatures specifies the heat rate that is transferring from the higher temperature all the way to the lower temperature. So Q dot equals temperature difference over R. So for example, for conduction systems, if you remember, we had heat rate equals to conduction constant K times area times temperature difference. Let me call it simply delta T instead of Ts minus T surrounding. And simply you can find the resistivity of conduction systems as temperature difference over Q, which is the heat rate. That would be equal to K over A times delta T is equal to 1 over K A. For convection, you had H, which is the convective constant, times area times temperature difference. And here you could find the convection resistance as temperature difference over heat rate. This is equal to delta T over H times A times delta T. That is equal to H times A. And for radiation, we have delta T over epsilon sigma times area times blah, blah, blah. So you can find the radiation resistance with this formula. And the same rules for combining heat resistances in the thermal systems is applicable as what we have for the electrical circuits. If you remember, in the electrical circuits, when you have some different resistivities connected together, and you have a high voltage to a lower voltage. Then for finding the total equivalent current that is uh, being transferred from the high voltage all the way to the lower voltage, you could add all of those resistivities together to find the total resistivity, and I would be voltage difference over the equivalent resistivity. Again, for thermal systems, you may have, for example, instead of voltage, you have temperature here. So temperature from higher to the lower temperature, and you can have different elements here. You can have conduction for the first resistivity, convection, and radiation, and those kinds of resistivities can be added up together to find the total amount of thermal resistivity, so that we can find the heat rate that is being transferred. That makes our problem much more easier, because if you want to find the local heat rate, then the local heat rate would be make us to solve our problem for each section separately. So basically, adding up these resistivities together makes our problem much more easier. There is also a point to be made out here. If we have parallel resistivities, which I'm sure won't come on your exam. For example, we have two resistivities parallel together. That happens in cases, for example, where you have an inner surface, an outer surface, and in between you have two materials. For example, you have iron, and also you have, I don't know, silver. And for each of those, you have a different conductivity constant. So in that case, basically you are having two resistivities that are being parallel together. They are not in line, they are not serial, they are parallel. So in this case, for finding the equivalent resistivity, you have to know that it can be calculated and based on the fact that I can derive the equation for you, or I can simply write it down. Simply writing it down will give you this equation: R1 times R2 over R1 plus R2. This is the equivalent resistivity of this system. But if you want to find the formulation yourself, you can find it based on the voltage difference and current that is applicable in this system. If you see a similar voltage difference is applicable on both iron and the silver here. So the voltage difference for both the upper and the bottom resistivities are the same. And we know that voltage difference is equal to resistivity times current. That is actually, in our case, temperature difference equals resistivity times the heat rate. And by knowing that, you can demonstrate that 1 over equivalent resistivity will be equal to 1 over first resistivity plus 1 over the second resistivity. That actually comes from the fact that if you have two currents that are being added up together, you have a current of I1 and a current of I2, and the total I is equal to I2. So the heat rate is also, the total heat rate of the system is equal to the heat that is going through the first resistivity plus the heat that is going through the second resistivity. That will change our problem to Q dot equals to Q dot 1 plus Q dot 2, and Q dot 1 is equal to temperature difference over resistivity 1. Q dot 2 equals to temperature difference over resistivity 2, and the total heat rate is equal to temperature difference over the equivalent resistivity that we don't know and we want to find it. So since the heat rate that is being splitted into two lines should be added up again here, so we can say Q dot total is equal to Q dot 1 plus Q dot 2, and based on that you can write temperature difference that is constant between the two points for each of those like terms over the equivalent R equals to the temperature difference over first resistivity plus the temperature difference over the second resistivity, and that will give us 1 over equivalent R equals 1 over first R plus 1 over second, and if you solve this, you will get R1 times R2 over R1 plus R2. So I hope this won't be, this will not be embedded inside your this final exam on Tuesday, but that was good to know, because you may be surprised sometime at exams. So basically knowing that, you can find the total resistivity between the inner space and the outer space. That is one way actually for finding the heat rate, but going back to our question here, so we had a pack of ice at the middle, and we wanted to find the rate of heat transfer to the ice water in the tank and also the amount of ice at 0 degrees of centigrade that melts during a 24-hour period. The first two sections, I will leave them out to you, and we will check that tomorrow. Please go and try to find the resistivities yourself. We have a problem. The next problem will be on finding the resistivities, and I think I also taped a video that was sent to you by Arsalan yesterday. It was also the way how we serialize the thermal resistivities and we add them up together for finding the heat rate in the main stream or line of the heat transfer problem. So for finding the rate of heat transfer in this question, what we first do is to find the area that is the outer area of the tank. the outer area of the tank is defined by pi times d of outer space to the power of 2. And we know that d of the outer space is equal to the inner diameter plus the width of the, let's say that was a stainless steel 2 centimeters thick. So 2 times the thickness, that would be equal to diameter of the inner space is 2 times of the radius, which is 1.5 meter. Plus 2 times the width, which is equal to 0.02 centimeters. That would give me an amount of 3.04 meters. And the outer space would be equal to pi times d of out 3.04 to the power of 2. That will be equal to 28 times 65 meters squared. So the first question was that was asked is this one: rate of heat transfer to the ice water in the tank. Okay, we have to put the heat rate that is being transferred to the ice as the combination of the convection and the radiation the convection is being made between the inner surface of the tank and the ice. So H times area times T of surrounding minus T of surface plus the radiation, which is epsilon times sigma times area times T of surrounding to the power of 4 minus T of S to the power of 4. So if you remember the heat transfer and convection heat transfer coefficient for the inner space was given as 80, if I remember, yes, it was 80. And the area was equal to 28.65 times the surface of the tank that was at 22 degrees, I think. So, if you put other terms here, because we want to cover 2 more questions that the concepts are much more important for me, I will leave this question out and we will come back to it later, maybe at the beginning of the class tomorrow. but the thing is, you have all the values. So if you substitute the amounts of epsilon, sigma, and area, and all of the amounts, you should get the amount of 23.1 kilowatts, and the amount of melted ice should be equal to, because as we saw for the nitrogen inside the tank in the previous example, the mass rate is equal to the total heat rate over the fusion is 23.1 kilowatts over the fusion that was given as here as 333 kilojoules over kilogram, and 333.7 kilojoules over kilogram will give me an amount of, let's calculate 23.1 over 333.7, 0.06922. That is basically watt. I know we know that watt is joule per second, so this is kilojoules per second. The unit will be kilograms over second, but it has asked me to find it in 24 hours. So by multiplying the second with, I know that each hour is equal to 3,600 seconds every hour, and each 24 hour will be equal to 1 day. So this amount times 3,600 times 24 should be equal to 5,980.94 kilograms per day, per each day. So I only wanted to give you the final answer of this question, but make sure to solve it again for yourself, because I might have performed some mistakes in it, as we did not put any amount of focus on the solution part. We focused on the concepts, and we went through resistivities in parallel and serial settings. Next question is, so we already have reached 7:30. We are now at 7:30, but we still have two questions to go. I think we can go for another 30 minutes if you are not tired, So next question is basically the one I think I have solved it in the video I sent yesterday, or it is very similar to what we had yesterday. It is saying that a window is consisting of 3 layers. So when you are being said that there are layers of like conduction, convection, radiation, basically you have to find the resistivity of different parts of your system, and then find the equivalent resistivity based on your system, whether it is a serial or it is a parallel system. So the question is telling me that the window has a 1.2 meters high. So this is the height of it, and 2 meters wide, which is the width of it. So what is it telling me? It is telling me the area. Area is equal for the window. It is equal to height times the width. So the area is given by the question itself. 1.2 times 2. That is 2.4 meters squared. And it consists of 2 3-millimeter thick layers of glass. The schematic of it is also depicted here. 2 layers of glass with conduction constant of 0.78 watts over meter times degrees of Celsius. And they are separated by 12 millimeter wide stagnant air inside that has a conduction constant of 0.026 watt over meter times degrees of Celsius. And we also are given the convection coefficients at the inner and the outer space with values of H1 is equal to 10, and H at the outer space is equal to 25 watt over meter squared times degrees of Celsius. And it is saying that we should disregard and do not consider any heat transfer made by radiation. And we are asked to draw the thermal resistant network, thermal circuit, and label the associated resistances and determine the following. So we first will depict the system as what the question has itself given us. So what we have is basically a window. There are 2 layers of glass with air inside, and the outer and the inner are denoted with convection terms of 125, the other is 10. So the amounts are not important. I'm going to draw the actually the resistant network of it. So there are 5 layers basically. First layer from the inner space that is held at the room temperature 0.1. From this point all the way to the inner surface of the window, we have a convection term. Between the inner surface of the first layer and the outer surface of the glass layer, there is a conduction term. Then between the 2 glasses, there is an air insulation layer with a specified amount of K that is much more lower in terms of magnitude with compared to the constant we have for the glass layers. Again, similar resistivity or resistant for the glass layer, the outer glass layer, and the convective layer at the end. So basically, there are 5 layers. If you want to depict them, we have to draw 5 resistances. The first resistance is R of convection. First one is R of glass, that is conduction in shape of conduction. The middle one is the air resistant, that is again denoted with conduction form of heat transfer. An outer R of glass, and again convection resistance at the outer layer. So each of them should be specified in order to find the equivalent resistivity of the whole system. What is really important and also very effective in terms of simplifying your calculations is the fact that you have to remove out the terms that are common between all sections of your calculations. For example, if you have area in all terms, it is really easy to remove it out because it won't give any new information to your question. The variables are important that are changing, basically. For example, you have convection, you have conduction. The conduction constant changes from one layer to the other. So this is really important. But the area is constant throughout the whole system because I'm solving the equation for constant area all the way from the inside room to the outer space at the outer surrounding air out of the room. So I want to include the area inside my resistances. That's why I can, for example, find the R of convection as 1 over convection constant, that is 1 over 10. And I think the unit is also important for mentioning when you are solving your question in the exam. Always remember to put down the units because many professors will reduce and decrease your score at the end if you do not include units. So the unit for convection or for any constant conduction or convection constant is equal to watt over meter squared times degrees of Celsius. So the unit for R of convection so my screen was, I don't know what happened here because somebody called me and the connection to the screen was lost. So let's go back to the notepad. So the unit for the resistivity is inverse of what we have for the convection constant. So that was watt over meter squared times degrees of Celsius. That is inverse of it, which is meter squared times degrees of Celsius over watt. So when you want to put the units, it is always easy to go back to the equation and see how other terms are behaving in terms of units. So that is the way you can find the unit for the coefficient you do not have any information on, based on what is your knowledge on other terms. For the glass layer, you have R of glass as oops, sorry, what happened? So everything, it seems like everything has gone out. So I will again write down the resistivity for the convection part. So R of convection is equal to 1 over H, so that was 1 over 10. R for the glass layer is equal to L over K times area. I won't include area here, so that would be equal to length, which was 3 millimeters over K, that is 0.78. This was the constant, the conduction constant for the glass, and this amount is equal to 0.00385. And for the next resistant, which is for the air layer, we have again length of the air layer over the conduction constant of it. The length was equal to 12 millimeters, and K was equal to 0.026. This is equal to 0.46, 1.4. R of glass at the second layer, at the second glass layer, is the same as the first one, so I won't write it down again. It is the same. You can do it also in your exam when you have a similar or same term. It is not necessary or required to consume your time on it. So this will be equal to 0.00385, and the outer convection between the outer surface and the surrounding air is equal to 1/25, which was the amount of H, and it is equal to 0.04. So the equivalent amount of resistance is equal to, let me write the whole equation again, R of convection plus R of the first glass layer plus R of air plus R of the glass second layer plus this second convection term. So adding these amounts up together will give me 0.1 plus 0.00385 plus 0.46, 1.4 plus 0.00385 plus 0.04. That is equal to 0.6924 meter squared times Kelvin over watt. So if we had included the area, that the unit at the end wouldn't have this meter squared, because all the denominators had that meter squared unit, and that would remove out it from our final answer. And the area can now be found as height times the length. Height was 1.2, I think, if I remember, and let me check it back again. So it is, yeah, the height is equal to 1.2 and the length is equal to 2 meters. So 1.2 times 2 is equal to 2.4 meters squared. And now for finding the daily rate of heat loss through the window in a static operation, we can use the formulation we had previously. So delta T times, so let me drive the equation again, because you have to know, you shouldn't memorize any equation. There are very simple equations for conduction, convection, and radiation. Try to drive them every time you want to solve your question. If you remember, for conduction systems, we had K times area times delta T over L. So as we remove the area from all calculations in when we wanted to find the resistivities, so now my resistivity was equal to delta T over heat rate when I had included area in my resistivity terms. And now, since I didn't consider it in my calculations for the resistivity, I have to include it here. Yes, because if you remember, R was equal to delta T over Q dot here for the conduction. That was equal to L over KA. And since we didn't mention A here, so our new R was A times the previous R. So when we want to find the total heat rate, we have to put temperature difference over R, and we have to add an area term here because we had removed it previously. So doing that, 2.4. So basically what I did, it was instead of multiplying the area every time in those terms of resistivity, I only put it one time at the end. In that case, I had to calculate it, and it could make my calculations much more like complex. But in this case, I only substituted in at the end, and it makes my problem much more easier. So 2.4 times delta T, which was 24 minus 5. Sorry, it doesn't work. I don't know why the pen is not working. So we have again lost the information here. So I will write it again. A times temperature difference over R, 2.4 times 24 minus 5 over the equivalent resistivity, which is 0.6924, should be equal to 114.24 watts. And the next part of the question was asking me to find the temperature of inner surface for this double pane window. So it basically means the question wants me to find the temperature at the second point. If you remember, we had 5 resistances and 6 points, because we have 1 point at the inner room, the other is at the boundary, two others are at the boundaries of the first glass layer, and there are 2 points at the boundaries of the second glass layer, and one is at the outer layer on the surrounding air. So it wants me to find the inner surface temperature, the temperature of the inner surface of this glass. That means to find the temperature at the second point. So it really only needs to know the resistivity between the first point and the second point to find the temperature at the second point, because the heat transfer rate is equal in all sections of my problem, in all sections of this, all layers of this system. So we only need to know the resistivity to multiply it by the heat transfer rate so that we can specify how much temperature difference is being embedded between those 2 points, basically. So going back to the notepad here, I can find the temperature at the second point equals to the temperature at the first point, which has the highest amount of temperature, minus heat transfer rate over area times the equivalent resistivity between those 2 points. So that will be equal to 24, which is the inner temperature of the room, minus the heat transfer rate, which was found previously as 114.24 over the area that was 24 meters squared times the resistivity between those 2 locations. And if you remember, it was 1 over h, basically, by 1 over h for the convection term, and it was 1 over 10. So 0.1 will give me a final temperature amount of 19.24 degrees of Celsius. So the question answers are heat rate is equal to 200 and sorry, let's go back to the yes, the heat rate was equal to 114.24 watts, and the final temperature is equal to 19.24 degrees of Celsius. One last question is still existing, and this last question is basically from the final exam of the year 2017. So let me see where I have it. 2017. Okay, let's go to the email Arsalan sent me. I think it should be there. Okay, if you can see the question number 10, it is saying that a steady heat transfer between 2 large parallel plates at constant temperatures of 290 and 150 that are 2 centimeters apart are being occurred, and assuming the surfaces to be black, So the emissivity rate is equal to 1. Determine the rate of heat transfer between the plates per unit surface area, assuming the gap between the plate is filled with different substances. A, it is filled with atmospheric air. B, it is evacuated. C, it is filled with fiberglass insulation. D, it is filled with super insulation with different conduction constants. So if you pay attention, for the first two cases where we have air or the evacuation, in both terms, in both cases, we have radiation, because when we have air or when there is no material or substance in between, radiation can occur without even the need for any medium in between. But when you fill it up with fiberglass or when you fill it up with an insulation material, then the way of heat transfer is basically the mechanism will be conduction, because you have filled it up with a substance. There is no distance between the two layers, between the two parallel plates. When you have air or when you have evacuation, there is a gap between those two layers. But when you fill it up with a substance or material, then there is no radiation. The only thing we have is conduction. So for this question, for solving this question, you have the information for the temperatures of the two surfaces, two parallel surfaces. You have the length between them, which is 2 centimeters. And it has asked us to find the heat transfer, the rate of heat transfer per unit surface. It hasn't given us the area as well. So it asks us to find it per unit surface of the area. So for finding that, for the first case, we have both radiation and conduction, because the air can be used for conduction heat transfer, and it also it also helps and it also allows the two plates to transfer energy in the radiation manner. So for finding the constants of conduction for each of the layers, the important thing here is that the question has not given you the amount of conduction coefficient, which is the constant K. So constant K is really dependent on the temperature of the layer you are talking about. When you are not given, the best approach is to find the average temperature and then try to, so we have the temperature at the first layer as 290 kelvins, the second is 150. So T of average can be found as 290 plus 150 over 2, that is equal to 220 kelvins. So based on so based on the temperature, the average temperature, we can go and read the amounts of K in the tables. So for air, for example, this amount is equal to K of air. Let me go to my notepad here. I don't have much space there. So So K of air at 220 degrees of Kelvin, 220 degrees of Kelvin is equal to 0.0198 watts per meter Kelvin. And air is a substance which is between the two plates for the first case, which was A, if you remember. So for the first case, you have the heat rate as Q of radiation plus Q of conduction. That would be equal to epsilon times sigma times T1 to the power of 4 minus 2(1) to the power of 4 plus K of conduction for the air times T1 minus T2 over the length. And we do not include the area because we are asked to find it per unit of the surface. And epsilon is equal to 1, as the question has said. And substituting the amounts will give us 1 times sigma, which is 5.67 times 10 to the power of minus 8 times T1, which is 290 to the power of 4 minus 150 to the power of 4 plus constant of conduction for the air, which was found 0.0198 for the average temperature of 220 degrees of Celsius times temperature difference 290 minus 150 over length of 0.02 will give me the amount of 372.32 plus 0.0198 times, sorry again, I have to reshare my stuff because again I don't know why it comes out of the screen every time one calls me. Okay, this amount is equal to 7,000, and that gives me a total amount of 510.92 watt over meter squared for the first air case. Second, for the evacuated gap, the heat transfer rate will be equal to the radiation section, which is the same, and the conduction term is equal to 0 because the K for evacuation is equal to 0. There is no substance or material to fill that space up, so there is no conduction. That will be equal to 372.32 watt over meter squared. And again, C for the fiber, for the fiber glass insulation. For the fiberglass insulation, we do only have the conduction term. There is no radiation, so Q of total Q will be equal to Q of conduction, and is equal to it is equal to K of fiberglass times delta T over L. So delta T over L is the same as we had here, which is 7,000. But this amount, which is the constant for the fiberglass, can be found based on the average temperature, which was 220. If you check it in the table, the K of fiberglass should be equal to 0.063. So 0.063 times 7,000 is equal to 252 watt over meter squared. And for the last part, you have super insulation. And for the super insulation, I think the question has given us the conductivity constant as yeah. If you see here, you are given with the amounts of K for different parts, so it wasn't even needed to find the average temperature because all of the information were given to me. So I will use this amount of thermal conductivity constant for finding the total heat rate. So 0.00015 times 7,000 is equal to 1.05 watt over meter squared. So reporting them all again. It is really good to report all of your findings at the end every time. It makes reading your answers much more easier for the reviewer. So for the air case, Q was equal to 510.92 watt over meter squared because we had both radiation and conduction, so it had the highest amount. For the evacuation, there was no conduction. We only had the radiation, which was equal to 772.32. And for the fiber insulation, it was equal to 252 by only conduction because there was no radiation in this case. And for the latter case, the final case, it was equal to 1.05 because there was no radiation, and the conduction term was also very limited to we had a low amount for the constant K, so that is why we have a low heat transfer rate 1.05 here. So this is the end of today's session. I hope you all have enjoyed this session. We will try to cover the rest of the concepts tomorrow. And let me know if you have any questions now. You can also send me the materials I might not have already, or also if any other questions you may have that are different from the ones I have solved, you can send them to me. Let me leave out my email address here for you. So m.cavan73@gmail.com. So this is my email address. If you have any questions, please let me know. And I hope you have enjoyed this session. Please go through the details and let me know if you have any other questions. I hope you all have good exam on Tuesday. And if you have enjoyed, just leave me a comment here. And thank you so much. I'm available if you have any questions. If not, we can end this session in a couple of minutes or even seconds if there is no question. Thank you so much, Kylie, David, and I really like to have Matthew's comment as well here. Thank you so much. So if there is no question, we will come back tomorrow again at 5 o'clock to go through the fifth and sixth chapters. I'm really sorry if my language was not satisfying at some points. I'm not a native speaker, so that happens sometimes. I will try to get better tomorrow, but I hope you all have a good weekend and enjoy your night. Thank you all and goodbye.
Yeah, thanks a lot.
Bye-bye.